everyone, my name is Hariggeesh. For my engineering dynamic assignment, I chose a real-world rigid body system. Right above me, my hostel room ceiling fan. To model the system kinetic properties, I estimate its total to be 4.5 kg. I measure the central motor hub radius as 0.11 meters and the length of each the three blades as 0.55 meters by treating the hub as a solid cylinder and applying the parallel axis theorem to model the blades as cylinder rods rotating about the fixed endpoint and calculate the total mass moment of inertia about the fixed rotation axis I0 to be 0.378 kg meter per square. To bridge the work energy method with impulse momentum, I divided the shutdown process into two distinct spaces. Space 1 is the work energy space. State 1 is the when fan is running at the steady maximum speed 25 radians per second and the power I is cut. State 2 is the moment the fan has cooled down just 2 radians per second. The kinetic energy lost during the deceleration is equal to negative work done by hair resistance and bearing friction over the total directional displacement. Space 2 is the impulse momentum space starting exactly from state 2 as the fan slowed down 2 radians per second to complete stop at the state 3 is experience final mechanical resistance by assuming the short linear stopping duration of approximately for 1.5 seconds. The angular impulse equation directly the remaining angular moment from state 2 to the average internal braking torque required to bring the system to rest. Now, let's critically evaluate this member. The theoretical calculation assumes a constant friction torque. In reality, include non-linear hair resistance Q over calculation significantly, reducing drag scale qualification with speed, meaning energy loss happen extremely faster at higher velocities. Neglecting this means our theoretical velocity drop slower on the paper and then it actually does the real life. Furthermore, we assume the blades are perfectly rigid bodies in reality. They experience elastic twisting and aerodynamic filters which absorb kinetic energy through structural damping. From a structural safety perspective, slow deceleration time of 1.5 seconds keeps the structural impulse force minimal, keeping the shear stress on the blade rivet well within safe torque limited for aluminum. However, it is an object itself friend, dropping the stopping time milliseconds. The impulse force spike dangerously, threatening mechanical failure at the joint. To optimize this system, I propose a design modification, implement aerodynamic blades profile with a variable pitch angle, reducing the blade pitch automatically. When power is cut, minimize aerodynamic drag during cost down, reducing press on the joint and allowing the fan to harvest its own kinetic energy smoothly if paired with generation